All right, so I'm going to be taking you through some review questions here leading up to the exam. This is for grade 12 college prep physics. We're going to start with kinematics. We're going to start at the very start, which was motion graphs. We had two types of graphs in this course that we used to describe motion. The first one was the DT graph. And that stands for position time graph, distance time graph, displacement time graph, whatever you want to call it, all right? And the two types that we studied were constant velocity and they always look something like this. Position is always on the y-axis, time is always on the x-axis, and a constant velocity graph always gives you a straight line. And from that straight line, you can get the velocity. V always equals the slope of that line. Another term used for constant velocity is uniform motion. And that did come up on our test. So constant velocity means uniform motion. The slope of the graph gives you the velocity or the speed. You can't really get the acceleration from this graph, and the area under the graph doesn't mean anything. So that's all I'm going to write about constant velocity DT graphs. Now, the non-constant velocities are accelerating. And they're always going to give you a curve on a DT graph. This would be an example of something that's speeding up because the slope is increasing. It's going from shallow to steep. In this case, the slope of the tangent equals your instantaneous velocity. But on this exam, there's no questions where you have to make a curved graph and draw a tangent. So there's no tangents to draw on this exam. So don't worry about thinking too hard about that. I'm not going to draw a tangent on this curve because you don't need that for the final exam. What else can we do with that, though? That right there is, this one here is speeding up. You could also have one that's slowing down. And that would look something like this. All right, it's going from steep to shallow, so that one is slowing down. Again, the area really doesn't give you anything, so we're not gonna go over how to find the area. Just like the constant velocity graph can also be called uniform motion, the accelerating graph or accelerated motion is also referred to as non-uniform motion. I think that's all we need to say about DT graphs. So we better move on to the VT graphs. All right, so VT graphs, and the V stands for velocity. We have the same two types, uniform and non-uniform motion, or constant velocity and accelerating. So let's first go over the constant velocity. So our constant velocity VT graphs will always give you a horizontal line. All right? If it's above the time axis, that means it's moving forwards. Below the time axis means it's moving backwards, but it's always going to be a horizontal line. In this case, the slope equals the acceleration. And for a constant velocity, the acceleration is always zero, just like the slope of a horizontal line is always zero. This time we do need the area because it gives us something, all right? In this case, the area equals your displacement or distance traveled if you need to find that. You can get it from the area under. The area of this particular graph would be a rectangle, length times width. And you just have to know the width and the length, and you multiply them together. It gives you displacement in meters as long as we're using SI units. for the accelerated motion, it's not going to be a curve like on the DT graph. It's also not going to be horizontal. It is going to be a straight slant. All right? And all the same rules apply. Slope is the acceleration. Rise over run. It won't be 0 this time. And area equals the displacement, except now that area is a triangle. Base times height over 2. And this is the most complicated shape you see in this course to find the area of. So it's not that big a deal. So on the exam, a lot of this is covered in the multiple choice where it just says, you know, it might give you this graph right here and say something like, what's that object doing, accelerating or moving at a constant velocity? So you have to know that it's accelerating. All right, something like that. What else do we have to cover? All right, so that covers motion graphs. Now we'll look at linear kinematics problems. This is a whole page on your kinematics test, so we better go over it. We can better go over a few of these, all right? All you need with you is the 5 kinematics equations. They're on your formula sheet. You get the same formula sheet on your exam, so it shouldn't be any problem. What you've got to be able to do is identify what you've got. As a car tries to stop, it goes from a speed of 21 meters per second to 0 meters per second in 9.5 seconds, all right? This is obviously a time. This is a V2. This is a V1. Nice and easy to identify. And then it says, how far did it travel during this time? So that is a distance. All right, I've got D, V1, V2, and T. So that's going to be equation number 2, as I call it, which is D equals V1 plus V2 times T over 2. On the exam, I expect you to show the formula. I expect you to sub into the formula, and then I just look for your final answer. So V1 is 21 meters per second. V2 is 0 meters per second. The time it takes is 9.5 seconds, and we're putting that all over 2. Then you go to your calculator, and you just type that in. 21, I don't need to type in plus 0. It's going to be 21 times 9.5 divided by 2 equals, and it gives me 99.75 meters, which I can round to 2 digits, which is going to end up being 100 meters. Let's try another one. A skier starts down a slope of 0.5 kilometers. That's obviously a distance, 0.5 kilometers. At a velocity of 4 meters per second. I know that's a speed, but I'm gonna wait and see if that's a V1 or V2. If he accelerates at a constant rate of 2 meters per second squared, it says accelerates and it says meters per second squared, that tells me that it's acceleration. Find his velocity at the bottom of the slope. So it wants me to find the velocity when he gets to the bottom if he's accelerating. So it's looking for a final velocity if he starts at that velocity right there. All right, so I've got dA, V2, and V1. That's going to be equation number 5, as I like to call it, which is V2 squared equals V1 squared plus 2AD. So V2 squared equals 4 meters per second, and that's going to be squared plus 2 times 2.0 meters per second squared times the distance. Oh, now we have a problem. 0.5 kilometers. Don't put 0.5 in there because 0.50 kilometers is equal to 500 meters. That's what I'm putting in there, 500 meters. You're going to get a value, but don't forget that it's V2 squared equals that sign. So you'll need to take square root at the end. So I'm going to go 4 squared plus 2 times 500 equals, and it gives me 520. Well, that's a ridiculous speed. He's not going to get to the bottom of the slope at that. You got to take the square root of that 520 and you get 22.8, or round it to 23 meters per second. So V2 equals 23 meters per second. A ball is thrown up into the air with a velocity of 16 meters per second. How long does it take for the ball to reach the top of its throw? Well, it looks like it only gives you one thing, the speed that it starts at. So I'm going to call that V1. How long does it take? Well, I know it wants me to find a time for the ball to reach the top of its throw. So we need to know a couple of things here. One, anything that's flying through the air, and we can assume that it's on Earth, accelerates at negative 9.81 meters per second squared. In kinematics, it's important to make down negative and up positive, and things do accelerate down towards the Earth, so it's negative 9.81 meters per second squared. The other thing is that when it gets to the top of the throw, it stops for an instant. So the V2 is 0. When you throw something up in the air, when it gets to its highest point, its velocity reaches 0. So I've got a V1, a V2, an A, and I'm trying to solve for T. Let me think here. I think that's going to be equation number 1, which is simply A equals V2 minus V1 over T. And I've got most of this, I've got everything but one thing. 9.81 meters per second squared equals 0 minus 16 meters per second over T. 0 minus 16 is negative 16. Basically, you're just going to take the time and move it up on the other side, and you're going to take the 9.81, the negative 9.81, and move it down where the T was before. So you end up with T equals negative 16 meters per second divided by negative 9.81 meters per second squared. You'll be left with just seconds. It's going to be 1 decimal something, but let's see here. Negative 16 divided by negative 9.81 gives me 1.6 seconds. I think that was actually a question on your kinematics test, if I'm remembering correctly. So that's how you're going to tackle linear problems. Identify what you have in the question, choose the right equation, and then see if you can do the algebra and use your calculator. That's all there is to it. There'll be a few of those anyway on your test, probably the same number we just went over. On the way to the cafeteria, oh yeah, two-dimensional problems. So we did cover this a little bit. There's one question on your unit test, and I'm pretty sure I guarantee you there's one question on the exam, okay? Way to the cafeteria, student walks 5.4 meters west, 6.7 meters north, and finally 5.4 meters east. It's not all in the same direction. It's not just forwards and backwards, so I can't just say forwards positive, backwards negative. I've got east, west, and north here. So I have to draw it. And if I ask you this on an exam, probably the part A will say draw the motion or something like that. Here's what you do. 5.4 meters west. Just write 5.4 meters. It says 6.7 north. I'm going to run out of room here, but that's okay. 6.7 north. And finally, 5.4 meters east. There's another 5.4 meters east. And so that's a good part A. But what it's also going to ask you is things like, in a part B, like find the distance traveled, all right? And distance traveled is just the length of the path. So I just add up all those little displacements, 5.4, 5.4, and 6.7. So I go 5.4 plus 5.4 plus 6.7 equals, and I get 17.5 meters. And then I don't know the order that you're going to be asked this, but from that is what you find your speed from. So let's say that it does this, in... Sorry for that interruption. Somebody came to the door, and I may have lost my connection. All right, so we're back. Distance is 17.5 meters. From that, you can get the speed, right? Speed is equal to distance over time. In this case, that's 17.5 meters, and then we'll just assign it some time. Let's say it does this all in 10 seconds. That'll be nice and easy to divide by. 10 seconds equals 1.75 meters per second. All right, but let's say there's a part C that says find the displacement. All right, now displacement is defined as the line from start to finish. All right, and in that vector diagram we drew, here's the start and here's the finish. So what is the displacement? The displacement is 6.7 meters north. All right, and I'll write that down here also, 6.7 meters. If I want to abbreviate it, I put these square brackets around it. Now from that, I can get my velocity, because velocity is not distance over time, it's displacement over time. All right, and our displacement is just 6.7. 6.7 meters north divided by 10 seconds equals 0.67 meters per second north. So you see, when you're dealing with two dimensions, you often get a different velocity than a speed. This is an average velocity and an average speed, and speed comes from distance, and velocity comes from displacement. Let's move on. That's kinematics. If you can do all that, you should do very well on the kinematics sections on your exam. All right. Let's go on to dynamics review. Dynamics means study of forces, the causes of motion. The types of forces that we dealt with in this course were gravity, and we called that F subscript G, and you can go mass times little g to find the force of gravity. We also dealt with the normal force. And usually the normal force, actually I think in all cases in this course, I told you it would equal the force of gravity, so you can find it the exact same way. On a diagram, that might look like you've got a box or something sitting on the ground, you've got gravity up. It's going to fall through the ground unless you have an upward force to balance that out, and that's what the normal force is. That's why they're equal to each other. Anything that's moving along a horizontal surface, and that's all we dealt with in this course, is going to look just like that. And they'll be equal to each other. We also dealt with spring forces, spring or elastic forces, and we called them Fs, I think. Sometimes I call them Fe for elastic, and they're equal to K times X. We mostly dealt with that in the energy unit, but you can also apply the force, the spring force here in the forces unit. K is the spring constant, or the stiffness of the spring, and X is how much you stretch or compress that spring. We also have friction. And friction is F subscript little f, and it's equal to mu, that's that funny U with a tail, times the normal force. Mu, or that U with the funny tail, is the coefficient of friction. And it more or less, either it has to be given to you or you're given everything else and you're asked to find the coefficient of friction. That's what we did in the lab. We graphed force of friction with the normal force, and the slope of it ended up being mu. That was also a test question, I think. All right, that should be good. That should cover us for most problems that we need to do in dynamics: gravity, normal force, spring forces, and friction. I mean, there's also applied forces you can call FA, but for the most part, that's what you use, okay? A 9.5 kilogram box, that's obviously a mass. We're going to solve some problems here. Has an applied force of 11 newtons on it. So somebody's pushing it or pulling it with 11 newtons. So I'm going to call that FA. If the coefficient of friction is 0.25, calculate the force of friction. All right, so friction is equal to mu times the normal force. Unfortunately, we don't have the normal force here, so I have to look over here. I'm going to draw a free body diagram. Lots of times you're asked to do that. It says that it's a 9.5 kilograms, so obviously it's going to have a force of gravity down. It's going to have a normal force up that's equal to that force of gravity. It's going to have an applied force forwards. That's equal to the 11 newtons. And it's going to have a force of friction backwards because, well, it says right in this question that it's going to have a force of friction. So let's expand this a little bit. and get the force of gravity. It's a little small, but I'm going to try and squeeze it in here. That's equal to m times g, which is equal, in this case, to 9.5 kilograms times 9.81 newtons per kilogram. And I'll punch that into my calculator. 9.5, 9.81 equals 93 point something newtons. I'm going to write it 93.195 newtons. All right, so that's force of gravity, and that also gives us the normal force, 93.195 newtons. Now I've got enough information to solve my problem here, okay? Because mu is 0.25. So all I got to do here is 0.25 times 93.195 newtons. So that number's still in my calculator, so all I got to do goes times 0.25, and I get 23 newtons for my frictional force. Draw a free body diagram. Already did it. Determine the net force on the box. All right, this is important. This is going to be key to us understanding this problem, determining the net force. Essentially, the net force will be what the unbalanced force is. So you take basically your forwards forces minus your backwards forces. I know that friction is 23, that's backwards, and I've got an applied force of 11 forwards. So my net force will just be 11 forwards minus 23 backwards, which is negative 12 newtons. That is the net force. You could also say that it's just 12 newtons backwards, but that's what our net force is. That means it's going to be accelerating backwards, which can be a bit of a pain, but just because you're going to get a negative acceleration here. All right, so determine the acceleration of the box. Here's another formula. F net equals ma. It's on your formula sheet. If you have the net force, it's equal to mass times acceleration. Or to rearrange that, it's acceleration equals F net over m. The net force is negative 12. The mass is still the 9.5 kilograms. If I punch that into my calculator, negative 12 divided by 9.5, I get negative 1.3 meters per second squared. You can also express that as newtons per kilogram, but more commonly expressed as meters per second squared. Here's this one here. 140 kilogram man stands on a scale in an elevator. What's the scale reading going to be in these various scenarios? Reading on the scale. Well, first of all, reading on the scale is the normal force. So we're always trying to find the normal force. And I said in this class, for the most part, normal force will equal the force of gravity. Now that's in what's called inertial frames of reference. So if this elevator is accelerating up or down, then that little equation there is not going to work. But if the elevator stopped, well then absolutely. You're just going to feel your normal weight, which is just Fg, equals mg, which is 140 kilograms. That's a big guy. That's about 300 pounds. Times 9.81 newtons per kilogram. Run that into my calculator. 140, 9.81, and it gives me 1373 newtons. All right. Next, it says, what about if the elevator is moving down at a constant speed? Doesn't even give me the speed. Doesn't need to give me the speed, okay? Because as long as there's no acceleration, all right, as long as the acceleration is zero, and it is zero if it's going at a constant speed, then the weight that you feel is the same. Kind of like you do feel a little heavier when the elevator first stops. You feel a little lighter when the elevator gets to the top floor. But in between, when it's going at a constant speed, you just feel normal weight, unless it's a rickety old elevator and it's not doing so well. When the elevator is accelerating up, because it's positive, at 2.5 meters per second squared, I gave you a formula called apparent weight. It's the weight that you feel when things are accelerating up or down, all right? And it's equal to m times g plus a, all right? So in this case, it's 140 times 9.81 plus 2.5. You're going to feel heavier when the elevator accelerates up, and we've all experienced that before. 9.81 plus 2.5 equals 12.31 times 140 equals 1723 newtons. One more scenario. Now it's accelerating down at 1.4 meters per second squared. Should feel lighter. It's like when you're at the top floor and when the elevator initially starts to move, you feel momentarily a little lighter as it gets up to speed. So same thing. If it is accelerating, you feel an apparent weight, which is m times g plus a 140 times 9.81 minus 1.4. 140 times bracket 9.81 minus 1.4 bracket equals, and I got 1177 newtons. Feels a little lighter. A little lighter. That's dynamics. Machines is like a part of dynamics, a study of forces, but it's an extension. It applies these forces to simple machines, getting force or speed advantages. And I'm going to start with the pulley systems. That was my favorite part anyway. And then we'll just move on from there. It says draw a pulley system with a mechanical advantage of 4. So if you remember how we do these, I go like that. I make a line. I make a big wheel, a medium wheel, and a little wheel. And I make another line here with some mass on it. Big wheel, medium wheel, little wheel. If I want a mechanical advantage of 4, I probably don't need to use all these, but I know that for an even number, I've got to start at the top. So I'm going to start my string right here, right at the top, all right? And then it's going to go around. So I'm going to go, let me just get a good vantage point here. It's going to go around this wheel, and there. You count all the strings that are pulling up. This one's pulling up. That one's pulling up, that one, that one, that one, that one. There's my mechanical advantage of 4. Now I want a mechanical advantage of 7. So I'm going to do the exact same setup. Line, line, big, medium, little, line, big, medium, little. This time it wants an odd number mechanical advantage, and that tells me to start my string at the bottom. Bottom's right here, so it's going up and around and around and around and around. I'm going to check 1, 2, 3, 4, 5, so I'm not there yet. Around and around. And then I count the strings pulling up. 1, 2, 3, 4, 5, 6, 7. There I go. An IMA of 7. Just like on your machines test, some similar questions to that on the exam where you have to count the number of strings, and then also questions where you have to draw them. So that's pulley systems. A lever. So now we're going to go through most of the types of machines that we covered in this course. I'll try and get it done. It's almost lunchtime here, and then it's going to be chaos. I'm going to go as far as I can. A lever is used to lift a car that fell off a jack. The pivot's 0.5 meters from the car. The pivot is 0.5 meters from the car. The load is the car, so my load distance is 0.50 meters. I guess I didn't have to write that down. An effort force, that's FE, remember, is applied 2.5 meters from the pivot. That's where all our distances are measured from, so that is our effort distance. And then I just follow the formula to find the load force, FL. I just go FLDL equals FEDE. And this formula can almost be applied as is to all the machines. You just change, the forces are the same, but usually you change what the distances are that you're measuring. So I'm trying to find load force. So I'm going to go FEDE over DL, which is going to be 150 newtons, which is a pretty weak force to only be able to lift with, but whatever. The effort distance is 2.5, and the load distance is 0.5. So the load force that you can apply using this lever is 150 times 2.5 divided by 0.5, which is equal to 750 newtons. And that's the point of a lever, to make lifting easier. Part B says determine the mechanical advantage of the lever. And that's a simple calculation. You can do it in two ways. Just as mechanical advantage, there is a different formula for ideal mechanical advantage and actual mechanical advantage, but we can use whatever we want here. Since the question gave me the two distances, I'm going to use IMA, ideal mechanical advantage, is equal to dE over dL. All right, where the effort distance was 2.5 and the load distance was 0.5. And that ends up giving you a mechanical advantage of 5. The wheel and axle. I promise on the exam it'll be obvious which one's the RE and which one's the RL, but you're essentially always applying this formula here where it says F load times radius load equals effort force times radius, effort radius. So what weight can be lifted by an effort force of that? So obviously that's FE. And in this case, it's a winch. So this is going to be my load radius. And this is going to be my effort radius, because the idea of a winch is to get a force advantage. So I need my RE to be bigger than my RL. What weight can be lifted? That's load force, by the way. What weight can you lift? That's the load that you can lift. So it's FL equals FE over RL. So that's going to be 67 newtons times the effort radius, 35, divided by load radius, 5.5. Can't do that one in my head. I'll have to run it through the calculator here. 67, 35, 5.5 equals 426. And that's in newtons. What's the mechanical advantage? Again, you can do it using whatever you have. Again, I'm going to go to IMA because the question gave me the 35 and the 5.5. The effort radius over the load radius, 5.5. So I got 35 divided by 5.5, and it gives me 6.4. That one might be right off your machines test. You'll have to have a look. Let's keep rolling with the machines. We're almost to the end here. Screwdriver is used to drive in a screw with a pitch. Pitch of 1.5 millimeters. I don't know if you remember that, but this is going to be well, it's a machine called the screw. The screwdriver drives in screws. It's holding a load force of 23,400 newtons with an effort force of 350 newtons. So I've got my FE and my FL. I've got my pitch. First it says determine the mechanical advantage of the screw. Well, it gives me the two forces, so I'm going to go to the other mechanical advantage equation, AMA, which is simply load force over effort force. It's like the opposite of the other one. So that's going to be 23,400 newtons divided by 350 newtons. This part of it anyway is pretty simple, isn't it? Just got to look at what you have and just go with it. 23,400 divided by 350 equals 67. There's your mechanical advantage. What's the diameter of the screwdriver handle? That's a harder question. That's a lot harder. Actually, let's extend the page a bit if we can. What's the diameter of the screwdriver handle? So we have to find the radius, and for that we need to know what we have to use here. It's FL times pitch equals FE times 2 pi r, which is the circumference of a screw. The pitch is the distance between threads on the screw, and we've got to go from there. We have everything except for the r. Just something that screws people up is they forget about the 2 pi, all right? So the load force was 23,400. The pitch, I can't remember what the pitch is, so I'll have to go back up and have a look. The pitch was 1.5 millimeters. And the effort force is 350 newtons. And it's times 2 pi r. So now I'm going to go back down here and solve this thing. So if I go this value times this value divided by this value, I'll have that equal to 2 pi r. And then we'll have to divide by 2 pi still. So I'm going to get a value and just show you what that looks like. 23,400 times 1.5 divided by 250 equals, and I got 100, basically 100 even. So I got 100 equals 2 pi r. There's a couple of decimal places, but it's essentially 100. Last thing I got to do is divide out the 2 pi. Divide by 2 pi. And I'll get a value of r divided by bracket 2 times pi. I've got my pi button on my calculator if you don't use 3.14. And it gives me 16 millimeters. Again, be careful. This is definitely the hardest one on the review here today because it says not what's the radius, it says what's the diameter. And the diameter, if the radius is 16, then the diameter is equal to 32 millimeters. All right, so that's a tricky one. I think it was on your test. You'll have to go back and look. I seem to remember marking that one. A lot of people had 16 as the answer. At the very least, it was on your assignment. Last one. Your job is to lift a piano. This is a ramp question. I like the ramps. Lift a 750-pound piano. That's the load force. That's what you got to lift up. 2.5 feet up into a doorway. That is the height that you have to lift this thing. You can only produce an effort force of 150 pounds, which is probably about what I can produce. How long a ramp do you need? Now, these ones are a lot easier. It's just FL times height equals FE times length of ramp. We've got everything except for length of ramp. So it's 750 newtons, no, pounds, times 2.5 feet equals 150 pounds times length. So I go this times this divided by this, that will be length. I'll run that last number for you even though lunchtime just started. I almost got done on time. Divided by 150 gives me 12.5 meters. Length equals 12.5 meters. That's it. If this works, I'll do the same thing for tomorrow. I'll cover energy and electricity. Last day, I'll cover electromagnetism and sound. And then on our fourth review day, you can review whatever you need to. Review from your tests or whatever you've got. All right, there.